Let's talk about hyperconjugation in this video. What is hyperconjugation? It's a stability effect and it's lower than that of resonance. That's important, right? So let's take an example and try to understand this. Show and then tell, right? Alkyl carbocation. What on earth is this? I think you understand the word alkyl. Carbocation, maybe you do, maybe you don't. So let's start with some sort of an alkane, okay? Alkane, which means that there are no unsaturations. And it's important that you understand this example and you'll understand the rest of the things that happen in this video very easily after that. So I've got a couple of carbons over here. There's a single bond between them. This one right here is a sigma bond. All the bonds in fact are sigma bonds right here. And this carbon has 3 hydrogens attached to it. And this next carbon has 2 R groups, it could be any groups, and something else I've put as Lg. Now what on earth is Lg? Can you guess? Well, it's a leaving group, because if this group leaves, then I get an alkyl carbocation. How? You remember these arrows from the concept of resonance and all of that? Well, 2 electrons, there are some reaction conditions that make it happen. We'll look at that later when we do SN1, SN2, E1, E2. Some conditions make it happen such that these bonded electrons, they both go on to this leaving group, which means what you have is the leaving group with a negative charge and this carbon with a positive charge. If you remember the concept of hybridization from chemical bonding, then you will notice something has changed drastically between this thing on the left and this thing on the right. What is that? You have an empty p orbital on this species on the right, which is a carbocation. What that means is an sp3 hybridized carbon over here has changed to an sp2 hybridized carbon. Okay, this is important. Do you remember this? Is this new to you? If it is, then please revise what happens in chemical bonding thoroughly and then come back and watch the rest of this. I will cover what is a carbocation, what is a carbon ion in detail later, but you need to understand this sp3 to sp2 thing, because there's an empty orbital and that's the heart of everything here. What is adjacent to this empty p orbital is a carbon that is bonded to a hydrogen atom. I know there are 3 of them, let's focus on one of them, this one right here. Okay, these 2 red electrons are bonded sigma electrons of this carbon hydrogen bond. There's a sigma bond. So these are 2 things that are important. Okay, empty p orbital that belongs to the carbocation and a sigma bond between carbon and hydrogen. And what happens is that these electrons can move around, go from here to here. Like, wait, what's happening here? Well, the idea behind this, why it happens is everything like everything else in chemistry, right? Energy. To lower the energy, this is what happens. So this is an enthalpy stabilized process, this hyperconjugation. And you'll notice I've written something here. It says P sigma hyperconjugation. What's happening is that these electrons from this sigma bond are moving around to this empty p orbital. Okay. So now to give you the theory, that was the show part, this is the tell part. What is hyperconjugation? It's an interaction between a sigma bond, carbon hydrogen sigma bond, and a neighboring empty p orbital, or a neighboring partially filled p orbital, or a neighboring pi orbital. What's a pi orbital? You know a pi bond. What's a pi orbital? Well, we have looked at this when we did MOT, and that's right. I know you have not done an MOT from the point of view of a system that has more than 2 atoms, but in reality, everything can be explained by the concept of MOT a lot better. So that's the same alkyl carbocation that I showed you over here, but in a maybe stylized manner. That same thing. There's a couple of R groups. There's a plus charge, carbon with 3 hydrogens. Okay, cool. So I'm focusing on the first example right now. That's easy to understand. Okay, neighboring p orbital, and these sigma electrons go there. So it forms this sort of a structure where now I've got an interesting double bond being formed. Double bond? Yeah, it's possible, right? If these electrons go from here to here, you'll notice that I didn't put this here, I put this here, right? Because it's going from these electrons to this p orbital. And I know you're like, there has to be some impetus for this to happen. Why would this happen? Remember, I told you that this effect is lower than that of resonance. So it is stabilizing, but not as stabilizing as resonance. Because for this bond to break, for this to stick around, it's a bit of a jump, right? Literally, the H plus goes away. And similarly, if it can happen with one H plus, it can happen with multiple of these hydrogens. So the more the number of CH groups adjacent to a carbocation, the more stable it's going to be. Yeah. So there are multiple possibilities with each H atom, and more the number of sigma bonds, higher stability. What sigma bonds? The carbon hydrogen sigma bond. That's important. Not the carbon bond. It's adjacent to this carbocation, the carbon sigma hydrogen bonds. All of this is summarized in this one diagram over here. These three things on top is what I drew, and this bottom part shows the MOT structure, which you don't have to worry about too much, but this is just to show you that, okay, empty p orbital has some energy, a filled sigma bond has a lower energy, but this hyperconjugation effect, that lowers the energy even further. That's what makes it stable. Now, what do you need to know? And this is something, the application part of it is the stability order, right? In a methyl carbocation, there is no adjacent carbon. So there is no hyperconjugation here, okay, in the first one. So compared to the others, this is going to be the least stable, okay. What is going to be the most stable? Adjacent to this carbon, there are 3 carbons, each of which have 3 CH bonds, CH sigma bonds. So this is going to be the most stable, and this is a tertiary carbocation. I know we haven't done what is a carbocation, what is a carbocation, but I think you may already know what this is. A secondary is a carbon that has 2 carbons next to it, a primary is that has 1, and methyl is nothing. So this is a stability order. So far so good. Let's step it up a little bit. I told you one case where there was an empty p orbital. What if you have filled p orbital? What do you mean by a filled p orbital? Think about it like this. A bonded pair of electrons, the second bond, the pi bond, is what an alkene is. So take the example of a propene, right? One-ene propene is the same thing. I'm going to expand this line diagram and write down the hydrogen atoms and also the double bond in between. I have drawn this to be the sigma bond. This is the carbon-carbon sigma bond, which is not a focus here, but I'm writing this anyway so that you know what's going on. And this right here, these are the carbon-hydrogen sigma bonds that I am going to be interested in. These right here. This and their interaction with this red pair of electrons, which is basically the second bond, right? You know how this works, right? The second bond is between these 2 p orbitals. Yeah? Okay, awesome. So when these interact, which is the pi bond electrons of an alkene, this bond right here, and the sigma bond of carbon hydrogen adjacent to this carbon, which means this and this right here, okay, that's what's interacting. That leads to hyperconjugation again. But this hyperconjugation is an order of magnitude less than the previous one that we saw. What do I mean by order of magnitude? If I take the strength of that to be say 100, then this is going to be 10. Yeah, order of magnitude different, but it's still stabilizing, and you'll see this in many different forms. I've given you a couple of examples, and I've told you that this is called pi sigma hyperconjugation. Things get a little complicated here because you need to understand MOT to be able to do this, and it's not required at the high school level. But the general idea is that, okay, there isn't an empty orbital. So then what is the direction of electrons? Now in this case, there's an electron-rich pi bond, and you've got a couple of electrons over here. So it's possible that the order of this, the direction in which these electrons move could go from here to here, but where do they go? So from the pi bond, they could go back to the sigma bond. Like, whoa, okay, that's interesting. Hence it's called pi sigma hyperconjugation. I'm going to leave it at that. These are the 2 different orbitals that they could go to. And maybe we'll talk about this when we do more carbocations, right? Or different forms of electron-rich species. Alkene is one such electron-rich species, electron-rich in terms of this pi bond here, second one. But the end result is that, oh, if you've got a carbon adjacent to this electron rich pi bond, that is going to be a lot more stable than when there isn't any carbon, right? So the stability order is, I've got a lot of methyl groups, that's what it is, right? Next to this double bond, more stable. Fewer methyl groups, less stable. Why? Because what is interacting is this, for draw this out separately, and these electrons, okay? And I know that I wrote over here something called pi star and sigma star. I think you know about this from MOT, but the energy stabilization here is going to be, I told you, an order of magnitude lower, right? If I took 100 to be that of alkyl carbocation, I'm going to just put it C plus, and then an alkene carbocation, not a carbocation, just an alkene basically, is 10, because the lowering of energy still happens. But of course, sigma star is going to have a higher energy than sigma, and a pi star thing is also going to have a higher energy than this, right? So that's why stability exists, but the stability is lower in case of alkenes. We'll stop this video here, and I know there are other cases of hyperconjugation as well, and we'll cover that when we look at, say, a benzyl carbocation, or when we look at more aromatic species and cyclic compounds. We'll do that separately. But an introduction to hyperconjugation, this is all you need. The end result, a carbon adjacent to a cation or adjacent to a alkene, if it has a lot of hydrogens, that is a stabilizing effect. That is called hyperconjugation. This effect, we're just going to go back to the first slide, which says it's lower than that of resonance. And yeah, that was it that was planned for this video. I'll see you around.